So we hear a ton about self-driving cars, right? But the biggest question isn't just about the tech, it's about trust. How can we ever be sure a car is safe enough? Well, the answer, and you might be surprised to hear this, has less to do with wrenches and sensors, and more to do with pure mathematics.
So let's start with a puzzle, the one that really keeps automotive engineers up at night. Can a car with totally flawless code and sensors that are working perfectly still be a danger on the road? And the answer is a huge, resounding yes. Figuring out why is the key to this whole thing.
And that brings us to this really fascinating concept called a perfect failure. This is when every single part of the system does exactly what it was programmed to do, but the result is still a disaster. We're not talking about a software bug or a broken part, we're talking about a flaw buried deep in the car's logic.
Okay, so to deal with this exact problem, the industry came up with a very specific rulebook. It's called a SOTIF, which stands for Safety of the Intended Functionality. It's actually a formal international standard, ISO 21448. And its entire purpose is to create a process for hunting down these perfect failures. The dangers that crop up when the car is technically working just fine.
Right. So how in the world do you find a danger you don't even know is out there? Well, you start by drawing a map. Engineers have to chart out every possible situation a car might run into, and then organize that world into what they know and, even more importantly, what they don't.
In this map, it basically breaks down every possible driving scenario into 4 big buckets. Over on the left, you've got the stuff we know. Area 1 is known and safe. Think everyday, easy driving. Area 2 is known and hazardous, like when a camera gets blinded by sun glare. We know about these things, so we can design for them. The real problem, though, is on the right side of the chart, the unknowns.
Area 3, now that's where the real hunt begins. Think of it as the "here be dragons" part of the map. It represents every single dangerous situation that the developers haven't even thought of yet. A deer jumping out from behind a weirdly shaped sign at sunset, or a strange reflection off a puddle confusing the sensors. Finding these hidden monsters is the whole point of SOTIF.
So it's one thing to have a map, but how do engineers actually, go out and explore this dangerous territory? Well, they have to go on an active investigation, the hazard hunt.
And that hunt follows a very strict cycle called verification and validation, or VNV. Think of it like a continuous search and rescue mission. First, they test. They use all sorts of clever methods like constrained random testing to push the system into weird, unknown situations. Sooner or later, they discover a new hazardous scenario, a clue from that scary Area 3. Then they classify it. They drag that unknown danger out of the shadows and move it into Area 2, the known hazardous zone. Once it's known, they can improve the system to handle it. And finally, and this is the most important part, they repeat the whole cycle, over and over, making that dark, unknown area of risk just a little bit smaller each time.
But of course, it's never that simple, right? The road to perfect safety? Well, it's not a straight line. It's often more like taking 2 steps forward and then 1 giant step back.
So at first, as they run that V&V cycle, everything looks great. The car gets safer and safer. With every bug they find and fix, the average number of miles the car can drive before something goes wrong goes up and up. Progress looks fantastic.
And then the product team adds a cool new feature. Let's say a more assertive lane-changing assistant. Well, that new chunk of code, as useful as it is, can create a whole new set of undiscovered problems. And boom, all of a sudden, the car's safety can actually take a nosedive because they've just introduced brand new ways for things to go wrong. So when you zoom out and look at the big picture, this cycle of improving, then accidentally making things a little worse, then improving again, creates what engineers call a sawtooth pattern. Safety climbs, then dips when a new feature is added, then climbs even higher than before. The overall trend is always up, but it's this jagged climb towards that final safety goal.
And all of this, the hunting, the fixing, the 2 steps forward, 1 step back, it all boils down to the biggest, toughest question in the entire industry.
But first, let's get some perspective. We need a benchmark. What are we even aiming for? Well, according to US government data, the average human driver gets into a crash about once every 500,000 miles. That's the number they have to beat. To even be considered safer, an autonomous car has to be way, way better than that.
So, after all the mapping, the hazard hunting, and that sawtooth progress, how do you know when you're done? When do you stop testing? Is it after 1 billion miles? 1 trillion? When does a company get to stand up and say, okay, it's ready? You can't just guess. You need cold, hard proof. And that proof? It doesn't come from a manager's gut feeling or a marketing timeline. It comes from math. The final verdict on whether a car is safe enough is delivered by statistics.
This thing right here, it's called the stopping rule. And it's basically the mathematical gavel that closes the case. To put it simply, this formula tells you the exact minimum distance a car has to drive without a single safety failure to prove with a specific level of confidence that it's met its safety target. It takes all the guesswork out of it. It's a calculation.
So let's translate that math into something that makes sense. Look at this. If you want to be 95% confident that your car is as safe as you claim, you can't just drive your target distance, like say 500,000 miles. No, you have to drive 3 times that distance without a single problem. Want to be 99% confident? You're going to have to drive 4.6 times the target distance failure-free. The numbers get absolutely massive really, really fast.
But wait, there's one last absolutely critical piece to this puzzle. Even driving those mind-boggling distances isn't enough, because it's not just about the number of miles you drive, it's about the kind of miles you drive. I mean, just think about it, right? Driving 3 million flawless miles in sunny, clear weather in California proves basically nothing about how that car is going to handle a blizzard in Colorado or a foggy morning in Seattle. For the testing to be valid, the miles you drive have to statistically match the real-world conditions the car is actually going to face. Engineers call this the operational design domain, or OD. If your test miles don't reflect reality, that powerful stopping rule formula is pretty much useless.
And that, really, is the magic of this whole SOTIF process. It takes this huge, fuzzy, philosophical problem, how do we deal with the dangers we don't even know exist, and it turns it into a rigorous, data-driven system of engineering and mathematics that lets you actually prove something is safe.
Which leaves us with one final, very human question. The engineering can build it. The math can prove, with 99% confidence, that the machine is safer than a person. The question is, at what point are we ready to believe it? When are we ready to trust the code more than we trust ourselves?